Hey, hello guys, I'm making this video in English today for a petition of a few guys that asked me if I can make the video in English. That's no problem. This is the Greenamp, the IPS driver board for a powerful audio amplifier. And I spent a few days. This is the fifth day, I think, a fifth or the fourth day, I don't know. Probably the fifth day that I've been doing the layout. I was really surprised that I was able to put it together that fast, because this usually take me longer than longer time to accomplish putting everything together. So the way I did it is that each individual component macro of this circuit, one sample LEDs, diodes, trim pot, transistor, resistor macro, I assign the identification number to that particular macro, so in order to make the connections faster, so I know, okay, this is R21, so let me check where R21 has to be connected to what, okay, one sample, I'm going to find the, let me see, any resistor here. One sample R22 is a 5.6K ohm resistor, so it's on the rail, negative rail from the power supply. So I'm gonna look for this one here, right on the component list to the right. As you can see, there is a component list that you can assign the identification number. One sample, let's go back, I forgot. Okay, R22, let's find R22. It's on the component list. It's R22 right here. And we need to see if this is in fact connected to the negative rail of the power supply, the connection. So we're gonna use the test, this one right here, just to see the continuity of that connection. So you can see we had the terminal connections here. We had the positive, the PD that goes connected to the amplifier, the ground, and the other part that goes connected to the amplifier, the ND. So this is the negative of the power supply. So I'm gonna click here with this test. As you can see, let me zoom here. It's like a little needle probably. This is just to check continuity, what is connected to that trace in particular. So you can see we have the C6 is connected, the capacitor is connected to this input, negative input, so to filter out probably ripple sound or ripple noise from the power supply. And let's see, the R22 has to be connected to this rail, so it has to be, that's my channel, sorry about that. R22, let's see, where is R22? Oh, right here. So we have R22 that is connected to this rail. As you can see, it's a pulsing trace showing what is connected to this particular trace that is flashing right now. It's sort of like a flashing. At the same time, there is one more connection that is connected there. As you can see, the next trace is this one here. You can see the connection right here. This is a little like it's a square, supposed to be a circular connection. It's a collector of one of the TO92 transistors. So right now KSA 992, the collector is connected on this rail right here. So let's check. Sorry about that. Let's check. It's kind of difficult to make a video in English when you are thinking. I'm not thinking in Spanish. I get used to talk like that. Hold on, let me drink my coffee. It's getting colder. Ah, man, coffee is good in the morning. All right, so we have the collector Q4. Let's find Q4. Q4 is this one right here. And we have the leads. I already identified the leads of the transistor. We got the emitter, collector, and base, and the collector is in the middle. So as you can see, it's already connected to this trace. So that means that I can now this already check. I just I type check, or maybe ready, or it's ready to go, but I just type check, so it's ready to go. And this transistor, the collector is check. That's fine, check for now. It has 3 connections, so you gotta verify this transistor 3 times. You gotta do it 3 times. Now we got the collector is ready, so I should type here collector, so I know that the collector is ready to go. This is basically new for me, the way I'm doing now. Collector is check. So on the table, on the component table, you will see that it says item number 28 Q4 KS A992 value. This is the component value. Component comment. Sorry about that. This is comment. I say component. It's comment. It's a PNP transistor. It's check on the pin numbers. Pin C. Sorry about that. Pin C. So the collector is ready to go. So I will continue doing that until all this fill it up, and I will know for sure that this circuit is going to be ready to go, and so I can order a few PCBs just to try it out. There is some stuff I wrote to DYaudio.com. I have no response yet, so I'm not sure. Maybe they are ignoring my messages, or maybe they are really busy. They don't have time. But like me, I do have a lot of time, but they do not have time. Probably they are working or something like that. So I will wait for their response. I'm not sure why they have not responded yet to my my questions. I just have two questions about the. Let me see. The first one is the input, the negative connection of the audio signal of this driver board, and the other question was, sorry about that. I think I touched the microphone by mistake. I forgot what was the question. It's on the DYaudio.com. Let me see. Oh yeah, the capacitor. I asked for the value of this capacitor. This is electrolyte or a film capacitor. The C9 is a 1 microfarad capacitor. I'm not sure if this has to be a electrolyte. Did I say that right? A capacitor. We have this one here, and I think we have this one here, 1 microfarad. Or I'm not sure if I might be able to fit a small one here. It's not a big deal. I think I can just bend the leads if that's the case. But I need to polarize, put a positive symbol of the capacitor. I don't think it's really needed. I don't think it's a big deal. It's a big deal. All right, let me go back to the. I'm going to show you the simulation. Let me open the. It's too much to cover on one single video. I don't think I'm gonna be able to cover all the things about this design and how I did it. Maybe I gotta make a few videos about this. Okay, we got the Greenamp right here. Okay, it's a really powerful amplifier, let me tell you. Okay, so we have the circuit here. We got the servo. It's already done. I forgot to type here the connections here. So this is the connection of the power supply. The circuit right here. I asked Mr. Pete Ostripper, what's the purpose of this circuit right here? It's basically filtering circuit. It's the equivalent. I'm sorry if I cannot pronounce some words correctly, but anyway, equivalent of a filter or 22,000 microfarad capacitor, so to get rid of the ripple from the power supply. So this is the purpose of this circuit right here, is to filter out the noise from the. Oh my god, my coffee is getting cold. Man, coffee is good in the morning, I'm telling you. So we have the positive rail, and we have the negative rail that's going to filter out the noise from the power supply. So this is the circuit of the. Sorry about that. I'm zooming out, zooming in. Sorry about that. There's a truck passing by. I'm sorry about that. I cannot. I'm not living in a building that is really high. So all right. So it's okay. Don't worry about it. So we have the connection, the PD positive, and the NAD, and the bias adjustment circuit. I think Mr. Pete, he explained that this bias transistor is from the Harman Kardon audio amplifier circuit. He took it from that design, and he used it on the bias circuit right here. Harman Kardon. I cannot pronounce Harman Kardon. Shit. Okay. Harman Kardon. Let me see. Harman. Hey, Harman Kardon. I cannot pronounce that. The audio amplifier. Amplifier. Harman Kardon. Anyway, one of these designs, the audio amplifier. All right, so let's continue here. So let me show you the simulation. I'm gonna do this. I'm going to save this simulation into Google Drive link into the description down below of this video, so you can download. I'm gonna attach the original schematic from Mr. Ostripper, so you can take a look at it. I downloaded some new ones yesterday that I'm really interested. I think I have them here. I have the Wolverine version 2-A. I think this is a lot simple than the other ones. You see how simple it is? It's really simple. It's really simple. Probably anyone can make this one here. It's really simple. It has the same servo and everything. Look at that same servo. We have that one, and we have this one here, the spooky amplifier. If you look at it, it's kind of like similar to the one that I'm doing. It's a little bit similar. It's not the same, but similar. It had the same circuit. We got the servo, about the same. Yeah, you see, it's not much changes. But I already have this file. I already have it. The spooky. It's right here. So I don't need to make this design anymore because I already got it here. The spooky. This one is ready to go. So I'm doing this one here from scratch. Okay, let me show you the simulation. So right now, this amplifier is capable of giving a lot of power, but of course that depends on your power supply. If you have a crappy design power supply, you're not gonna be able to get the power that you want from this design. You need to have, okay, this is up to 530 watts, but think about it. You need to have a 1 kVA toroidal transformer and a nice capacitor, bank of capacitors to enable that power. But don't go crazy. Don't think about that. Just, I mean, you can have this amplifier working with just a 500 VA toroidal transformer. Is fine. You're not gonna push the amplifier to its limits. You just 500 VA, a nice bank of capacitor, well-designed power supply, and that's it. That's all you need. I mean, you don't have to go crazy, but keep in mind that to get power, you need to have a huge. I know there is formulas for that, but I mean, I'm talking just from the surface. But there's a lot of formulas that you can use to calculate the toroidal transformer that you need, the VA. The VA formula. I mean, it's kind of difficult to explain that. Anyway, 500 VA, probably 600 will be just perfect because you're not gonna push the amplifier that much. You don't go crazy. This for listen to soft music. You don't have to go crazy. Okay, right now, let me turn on the simulation. Right now, let me see. Okay, there's a sine wave right there. I noticed that it's pretty clean. It's pretty clean on this design. It's nice and clean. That's what I noticed the other day. You see the sine wave is pretty nice and clean. We got distortion is 0.002%, and we got 58 watts. I need to see how low it's going to be. Let me see. Okay, let me see. Oh yeah, you can increase, but I keep it that way. I'm gonna keep it just like the schematic. The negative feedback resistor, I'm gonna keep it like that. Maybe you can increase the negative feedback resistor to get more power, but the problem is that you will increase the THD. The distortion is going to be a little higher. So that right now, the last simulation we had 0.002%, But if you increase the negative feedback resistor, this R28 is, I'm going to show you in a minute. R28 is this one right here. R28, negative feedback resistor. So this one is 22K, the original value. So you can increase it to get more power, but the distortion is going to be higher. So right now we tested with 1 kilohertz sine wave. The amplitude is one volt peak, and let's see how it's gonna respond with that resistor. Change it to 47K. Let me see. Let me turn on the simulation. So we had 257 watts right now. Distortion is 0.003%. Sorry about that. Did I say that right? 0.003%. Nah, yeah, you can see we have more power, but the distortion is going to be a little higher. So that depends on what you want. You want more power, you want to sacrifice a little bit of THD, you can do that. Let's see how it's going to respond. If I increase the amplitude, I'm going to increase it, the amplitude of this design. Okay, 1.1 volt. Let me see. 311 watts. Let's see, 1.2 volt, 369 watts, 370 watts, 1.3, 400 watts, 1.5, and 1.4, sorry about that. 500 watts right there. We got 500 watts by just changing that the resistor, but the distortion is you're going to sacrifice the distortion is 0.005%. So that's depending on what you want. You want to make noise, there you go, you can make noise. But the original value is 22K on this design. So let me change it back to the way it was before. So okay, let me continue here. Let me explain you something here right quick. Let me see if I can do it with paint. Should I do it with paint? No, I don't need to do it with paint. Okay. Let me... full screen. Full screen is fine. Alright. The way I did it, mentally, I trace a line. I know that this is the input right here. This is in right here. Input, and this is the negative. Sorry about that. I messed it up already. This is the negative. And this is the positive. Input, sine wave, audio signal. So I trace a line in the middle. And I start to put it together on the layout. I started from this circuit, and then the other circuit, the half of the circuit. And then I'll continue placing the components little bit by little bit until I complete all the circuits. So we have six circuits right here on the same PCB. So we have this, the input circuit, and we have the servo circuit. So right now I'm checking this area has to be complete, and then I will continue with the other one, check to make sure that everything is 100% complete, and this resistor, and then I will continue with this one. After this is done, all this circuit, I will continue with the servo. Then from the servo, the input connections, this circuit right here, and lastly this one, or maybe vice versa. It does not matter. The most important thing is check the circuit, this circuit right here, 1, 2, 3, 4, 5, 6. Anyway, after everything is checked, that means that the circuit is done, it's complete. So what I'm doing right now is each individual macro has the ID. It's kind of difficult to explain that. I'm telling you, it is difficult, man. All right, okay, let me trace a line. Sorry about that. I'm telling you, man. Okay, let me trace a line and show the grid. Show the grid. Let me see. The grid is on. Oh yeah, I forgot to change the grid. It's too high. There you go. The center of this. There you go. Right here. Place a line. Right here, the middle of the PCB, just to show you. Okay. There you go. Okay, I have a line. So this area, all this area from this line to here, is the negative part of the circuit, and this area is the positive. So what I did, I just placed the components. This component, no, sorry, but let's start with the positive. The positive, I start to place the component here, but I had to pay attention to where the PD and the positive has to be connected to the amplifier. So I just place the power board here. This is the power board output, OPS, right here, and I place the PCB just to make sure that I have the correct connections right here, as you can see. So this is going to be connected by wire. I don't think it's gonna align correctly, but it's okay. It's okay. So it's going to be connected like this. I don't think it's gonna be straight, but that's okay. It's going to be connected by wire, so don't worry about that. I just needed one wire here, but it's okay. So right here, there you go. So that's the connection, and we need the negative feedback of this circuit. The wire that goes to the negative feedback is this one right here. This is the negative feedback. There you go. That's a piece of wire that is going to be connected here to the negative feedback. And then I think there's another ground. I'm not sure. This is G1 ground. This is G1 ground. Okay, G1 ground. I think I can place the wire, the ground wire. Should I need it? Let me see. Because the ground is already there, so I don't think I really need it. I don't think I need that. So that's the connection right there. Okay, let me go back to the explanation. So each individual macro here has the ID identification. So that's the way I did it. One sample, I had a plain macro that I just placed here. Let me disintegrate it. Okay. When you copy or place the macro and you start from the first component, one example, let me do the R20 1K, RK120. Sorry about that. Did I say what? R20 1K. So this one, I'm going to right click component and it's ready to go. So this is, I'm gonna do R20, assign the identification, and this is a 1K resistor, and then press OK. And then I forgot to show the visible value of the ID of this particular component. So it's ready to go. And the advantage of doing this is that you are creating at the same time that you assign the ID to any particular component on the circuit. You are already making the bill of material, the bill of material is going to be generated right there. So that's an advantage of doing this, of assign the ID to each individual component. As you can see, we had two because I just create that one right there. So if I delete it, you're not gonna see it. Wait, hold on, wait, give me a second. Hey, wait a minute. Wait a minute. R20 1K. Wait a minute, but hold on, I got confused. Why I have, okay. R20 5.6K. Oh, I was looking at the leach amplifier. Oh, Lord Jesus Christ. You see what I mean? Oh my goodness. All right, so we have R20. It's a 5.6K. So we had two. Okay, now I'm good. I'm good. R20. R21. What the hell I'm doing here? I already got confused too. R21, Jesus Christ. R21, there you go. Why I have R21? What the hell? 560. Oh, because you see what I mean? You see what I mean? I was looking at the other circuit and I got confused. You see what I mean? I got really confused. So now I'm on track. This is 560. So that's a good thing about giving the identification number to the particular component. So you know, in fact, that you're not gonna mess that up. There you go. There you go. You see what I mean? Okay. Now that I have, I'm trying to explain this in a better way. Oh my God. Oh Jesus. To be honest, I'm not sure if I'm gonna upload this video because this is way too complicated to explain. Anyway, I shall continue. I'm gonna continue anyway. Okay. The PCB is kind of small. PCB is kind of small. You can make it bigger, 100 millimeter by 100 millimeter. This is a 76 millimeter by 100 millimeter. I wanted to keep it at that size, just like the Wolverine PCB. Let me show you the Wolverine PCB. I'm gonna continue anyway. I already messed it up the video, but I'm gonna continue. What can I do? What can I do about it? It's too much to cover, man. I'm telling you. So this is the Wolverine PCB. It's similar to this one here. This circuit right here. About the same size. You can see right here. This one is created by J.K. Uteman from DIYaudio.com. So, and this design, I made a mistake. And I soldered some component that I really don't need. That's why you see this like this. But I already know that I don't need to do that. So, also here, I install component that I really don't need, so that's another mistake. And this is the negative feedback. This is the negative feedback connection for the power amplifier, and this is the output, the lateral MOSFET audio amplifier. So now that I have all this connected, I need to keep working on it. Check for bugs, because on the last video, probably you saw that bug. You'll be like, why the hell he put a bug on the PCBs? It's because I need to check for errors, mistakes, wrong connections. That's what I'm trying to say. So that's the way it is. At the beginning, you will look at the circuit. You'll be like, oh man, this is so complicated. How the hell I'm gonna do that? Just look at it, you know, step by step. You will do this circuit here first, the other part, and think about it. This is a half. Think about it, that this is the half of the circuit, and you will start from the positive, the servo, the input connection. This right here, this circuit for the input audio signal, and then you will continue the negative area, this area, and the other one. And it's not easy to explain. It's not easy to explain. So we had the ground. We had the test. We had the ground. I already know what is connected to it. We had the supply voltage for the servo. Is this one here, the circuit? We had the, I think this is the positive. We had the negative. We had the filters for the servo. This is the output. We had the positive end and negative end, and this is a trim. I'm not using the trim, and this is not connection, and this is negative, positive, and let me see. Oh yeah, really important. When you're doing an audio amplifier, you need to check on the data sheet of this particular transistor. For example, this is the KSA992. So you gotta go online, download the data sheet of this particular transistor, and look for the pins. Look for the pins identification. Let me see. I think I downloaded those the other day. Let me see. KS, BC. There you go, right here. This is really important, guys. Really important, because if you think that all transistors they have the same pins, you're gonna mess it up. Okay, there you go. KSA992. Pin number 1 is the emitter, pin number 2 is the collector, and pin number 3 is the base. So it will be emitter, collector, base. So emitter, collector, base, and I just type this, you know, the letters emitter collector base. So now know that this one in particular, this is the emitter, this is the collector, and this is the base. And then the only thing you gotta do is just figure out where it has to be connected. One example, let me go to, what transistor should I choose? Let's choose this one here, the QA. Let's see, the emitter, where is connected to it. So let's check QA. QA, it should be here. Okay, there you go, QA. Okay, let me check out again the schematic. Okay, emitter QA goes to R23. Emitter goes to connected to R23. We got the emitter here. Let's check this trace. As you can see, it's connected to one resistor, R23, right here. And the R23 should be a 100 ohm resistor. So let's check. Okay, R23, 100 ohm resistor. Check. It's already checked. And it's connected to the positive rail of from the power supply. There you go. So that one is checked. So that's the way you do it, little bit by little bit, until the circuit is complete. I'm gonna risk it, I think, to order a few PCB just to try it out, this design. But it's a little bit risky because yeah, the creepage. I know, Mr. ST, the creepage is really important. I'm not using the creepage for now. This is risky. Maybe it's a 99% that I might have an error on the circuit, but it's risky. That's why you gotta keep checking until it's complete, all the connection. But hell, you know, if you don't practice, you might never be able to accomplish how you say a good design. A good design. It's risky. I know it's risky because I'm not an engineer. I am not an engineer. I just hobbyist. I like it. Probably you see why my videos are kind of weird, because I mixed it up with memes and Warframe, stuff like that. It's just, I just want to be different, that's all. And this is my pet. This is my pet of the game, so it looked like similar to the banner of my channel. So it's risky. This is risky, guys. I don't know, but it's not that expensive. I mean, it's like $22 probably, maybe, just to order a few PCBs, 5 PCBs. I don't need that much, 5 PCBs to try it out. And yeah, that's it, guys. I'm gonna stop the video. I think I'm talking way too much. All right, I hope you like this video. Subscribe to my channel. I will continue. I'm gonna try to make another video to explain it better. It's not easy, man. I'm like I said, I was really surprised that in just 4 days I was able to put it together that fast. Because usually, like I already mentioned that. God damn it, I already say that. I mean, in 4 days I was able to put it together that fast. I'll be like, God damn, Jesus Christ. All right, guys, have a good day. I hope you like this video. I will make another better video than this one. All right, I hope you like it. All right, bye.
Do you remember the old war, operator? Ordis seems to have misplaced those memories.